All right. Hi, everyone. My name is Raphael, and that looks terribly corporate. The reality is I'm just someone who is deeply passionate about secure messaging. I've been working in that field for the past 15 years. Hello? Yes. Roughly 15 years ago, a new company came into existence called Wire. Maybe some of you remember the Wire Messenger. So I was a part of that, and I was in charge of security. That is what sort of roped me into this world of secure messaging. And I worked on open sourcing the source code of Wire, introducing end-to-end encryption. And then finally, I started working along with other people from academia and other companies on a new end-to-end encrypted protocol called MLS. So the first part of the talk is going to be about that. So you've probably heard of some of these encryption protocols. PGP for emails off the record was a thing roughly 20 years ago. Signal, of course, needs no introduction. So MLS is in some way the continuation of that. Just to put it a little bit in perspective, it would take a longer talk to actually explain how it works. There's a lot of information on it online, but I want to give the highlights here today. So one of the reasons we did it was that there was a very good precedent, the Signal protocol, but it was never fully openly specified how it works. There were no permissively licensed implementations, so it was very hard for other products besides Signal to actually use that protocol. And another incentive was that encrypting in larger groups was very expensive. So these are the two things that MLS is trying to achieve really well. So we brought it to the IETF, the Internet Engineering Task Force, and since 2023, it is now RFC 9420. So it's been fully specified over the course of 5 years. It supports post-quantum encryption, which is going to be the norm going forward. But we're in a period where this is, where we see protocols switching to post-quantum encryption. It's the first protocol to also implement post-quantum authenticity besides just confidentiality. And as I mentioned earlier, large group scalability is a lot easier with MLS compared to other protocols. I'm going to go very quickly over the security properties. This is a little dry, so I'm going to try and put this in simple terms. So end-to-end encryption means that messages are encrypted between user A and B, and that gives you confidentiality, and authentication means you know who actually sent the message. Then there are two terms, forward secrecy and post-compromise security, and those are a mouthful. We're going to get back to that in a second. And finally, MLS introduces something that has never been there before, and that is that members of a group chat cryptographically agree on who else is in that group chat. So if I send a message to you and you receive that message and you can decrypt it, then you have some proof that I see the same set of participants in that chat. And also slightly more informal, it helps with transcript consistency to a certain degree. So going back now to forward secrecy and post-compromise security. So we said earlier, end-to-end encryption is encrypting messages between user A and user B. And such an encrypted session could last for a really long time, potentially years, when you talk to people over time. So it is not a bad idea to consider that one of the endpoints, one of the devices of the users could get compromised in that time. And when you get compromised, your key material leaks. And so, for example, for email encryption, that means that if I get my hands on a private key, I can potentially decrypt years' worth of encrypted email. Or in the other direction, I can keep decrypting them in the future. So this window of compromise should be as small as possible, meaning if key material is going to leak, then we should actually not like limit the effect that has. And this is what forward secrecy and post-compromise security means. This is what happens before and after this window of compromise. And finally, about the efficiency, this is a graph where the red line indicates what efficiency you have in large groups with protocols like the Signal protocol that is inherently linear. So the more people you have in a group, the more expensive the encryption is. And here's like an extreme example of a group of 100,000 members. So you would have 100,000 operations to do if you were to do that linearly. With MLS, it's logarithmic, so you would only have to do 17. So that's a lot more efficient. So these are some of the companies and also academic institutions that have been working on MLS. And to put that in numbers really quickly, we have some large deployment these days. The most recent one is between Google and Apple. They, a few weeks ago, they started encrypting the successor of SMS messages called RCS between Android and iOS using MLS. So going forward, that is going to be end-to-end encrypted, which is nice. Discord is using MLS to end-to-end encrypt calls. And Cisco WebEx has been one of the first movers back in 2021. And you can enable end-to-end encryption in WebEx. And Wire has also been active in that space and has adopted MLS for its users. And then there's a much longer list of smaller or bigger integrations, some of which are still ongoing. You might recognize some of these names. I suspect some of you have a background in Web3, so there's also things like the World app and Coinbase app that use MLS for end-to-end encryption. So MLS has been standardized since 2023, and however, the ecosystem is still active, and research is still being done to extensions of MLS. For example, we've been working on a variant called DMLS, decentralized MLS, for environments where you don't have a central instance necessarily. We've been working on making post-quantum MLS more efficient as well. Then making MLS more suitable for scenarios where users have several devices that count as ends in an end-to-end encrypted scenario. And finally, we're also exploring how MLS can be used for transport encryption. The last slide about MLS, OpenMLS, this is our implementation in Rust of the protocol. So that's an open source library, permissively licensed. It's being used in some of the products you saw earlier on the slide. And this is also our building block for AIR. So AIR, this is the very first time that I speak about AIR publicly in a talk, so this is exciting. It's very early days for AIR. It's a new messenger, obviously based on MLS. And so you might ask, why even do a new messenger these days? There are so many already. But for a while, we've felt that something is still missing and that there's a sweet spot that is not really covered. And so we care a lot about privacy, so this is important. We also care about decentralization. It's a vague term. It means different things to different people, but the bottom line is probably we can agree that it's the opposite of centralization. And what's also important is feature richness in a messenger. People want to not have a steep learning curve or miss certain features if they switch to another messenger just because it's private. And finally, robustness. And I'll get back to that, what that actually means. So AIR is essentially trying to combine these four things in a way that we think has not been done before. So of course, end-to-end encryption is done with MLS. Everything is end-to-end encrypted. That's the baseline these days anyway for secure messengers. The content, the read receipts, the delivery receipts, anything that is being transferred. and we are in the process of transitioning to post-quantum resistant encryption. The more interesting part is now about identifiers. So this is where we deviate a little bit from other solutions. So with AIR, you do not need to have a phone number or an email address to sign up. You don't need anything, in fact. We have usernames. Those can be chosen freely, and you can have more than one, up to 5 currently. And so the interesting part is that the usernames are actually not directly linked to accounts, because the usernames are potentially the one element that can be identifying if you pick your real name as a username, as many people would do. It's interesting to not have that associated with the account, so that in the event where data becomes open because it was hacked or because it was legally required, then you cannot conclude anything from usernames. And more generally, metadata. So we try to avoid storage layer metadata. That sounds complicated. What that means is it's very similar to Signal, where essentially there is no plain text record of metadata on the servers, at least the kind of metadata that would be problematic. So what do we mean by metadata? That is, for example, who talks to whom in the context of a messenger. And also other stuff like how often do people send messages, at what time do they send messages, etc. So aggregating all this data is something in the context of surveillance that is very powerful, because you can draw a lot of conclusions just by looking at metadata, even if you cannot decrypt the actual content of messages. So we're very focused on protecting metadata. But finally, robustness. So protecting metadata, to a degree, it's not that complicated, because you just don't store them. You make sure that messages, for example, they have enough data attached to them so that you can route them from like user A to user B or in groups. But you don't necessarily need to store that. However, if you don't store it, then you run into the problem that certain things become a lot harder than they used to be when you don't have metadata. For example, denying access. If you want to block a user and the server doesn't have any concept about who's talking to whom, then that becomes hard, because the server cannot effectively block users in the simple fashion it could do if there were metadata. And the same is true for rate limiting. For spam, for example, like how many messages can you send to another user per hour? If the server or the general infrastructure through which the messages go has no concept of that. So, and lastly, recovery. If you lose all of your devices, you want to recover your account. Like how do we do that if the server doesn't know who you were talking to previously? So these are the really hard things to solve if you want to get rid of metadata in a way that you do not affect the basic security functionality that you actually expect from any messenger, meaning blocking people, not receiving too many messages, not receiving too many contact requests, etc. So this, in other words, this took a while to figure out. And then decentralization. So it turns out that it's actually great when you don't have a lot of metadata. Then it becomes a lot easier because you do not have a lot of data in general on the servers. And in an end-to-end encrypted messaging system, most of the logic actually happens on the client side. So this makes it easier if you want to decentralize things. And so without compromising robustness and security, it is comparatively easy to have something that is federated, for example. So this is something we are aiming to achieve in AIR. So we are in the Apple App Store and the Google Play Store currently with an early version of AIR. So we cover mobile platforms already. Soon there will be desktop versions for Windows, macOS, and Linux. Hopefully it's a matter of weeks at this point. And then very important, we are free and open source. The core, which is actually most of the messenger, is written in Rust. And then there is a relatively thin layer of Flutter on top of that for the user interface. And this also allows us to have the same code on all of the platforms, which is important because we are a small team. So we need to be efficient about what we do. So we have a relatively coarse roadmap at this point. The next thing is going to be desktop support, and then we want to catch up with all of the popular features, from other messengers, muting chat, share extensions, reactions, etc. There's still quite a few things missing. This is also going to be driven by what the community wants and the community needs. We want to make self-hosting easier so that anyone can actually host an Air server so that we are not the only operator. This is how we think we can contribute to decentralizing things. And last but not least, calling. This is probably only going to happen next year. So audio calling, video calling in one-to-one and groups. Then we're exploring something that an app called Linear has introduced recently, and we thought the concept was super interesting. A zero bug policy. Of course, that's a lie because we all know that software never has zero bugs. But the idea is that we want Air to be really reliable. It should work well. And so if we know about a bug and it's really reproducible, then we want to fix it quickly. A little bit about funding. So I mentioned earlier, we're a small team. And so the company that is working on Air is called Phoenix R&D. And we did not take up any VC funding. We saw that with other messengers, we think it's fundamentally not really compatible with developing something private. So that's why we decided to do it differently. Instead, we are financed through grants from the usual sources like the Open Tech Fund, the Sovereign Tech Fund in Germany, Prototype Fund, NLNet, etc. And so the most important feature last, in 2026, any software needs to have a dark mode. So Air has that as well. And this concludes my talk. So if you want to learn more about Air, if you want to try it out, the domain name is air.ms. That's where the QR code is going to point you to as well. It's invite only for now. And so I'm happy to hand you invite codes. Also, my colleague Julian, who's sitting there in the back with an orange lanyard, has some more. So thank you for listening.